We're going to start by sketching 4 graphs here. So the first one we'll do y equals b to the x, where b is greater than 1. If you think you can sketch it, do it. So what does the exponential function look like? It looks like this. And we're going to talk about the domain and range. It's really easy to mix these up between logarithmic and exponential. So visualizing the graph, I think, is a good way to get them right. So the domain for the exponential function is x is an element of the real numbers. X can be anything. In other words, any input. X is in the exponent. You can put whatever you want in there and it will work. You put positives, negatives, fractions, 0, whatever you want. But the output is not the same. We're never going to get 0 or negatives as our output, no matter what we throw at it, right? And this has a horizontal asymptote at y equals 0, which may or may not be useful. Might be. Okay, whoops, I made that one way too big. Next one. So if the base is between 0 and 1, some kind of fraction like a half or something like that, the nice thing is it doesn't change any of those details. Domain and range is all the same, but the graph does look different. It's decreasing now, the other one's increasing. Okay, and can you draw this? Log base b of x. And again, we'll do b greater than 1. That should be a b, not an x. Maybe something felt weird about that. There we go. The base. We're talking about the base there. The base is between 0 and 1. Do you remember what the logarithmic function looks like? Yeah, we haven't seen it that much like in MHF you do, but it's not as common for us. And we know that exponential functions and logarithmic functions are inverse of each other. So what does that mean about, oh, I've totally messed up the spacing on this. Okay, so the domain and the range, if this is the inverse of the exponential function, what does that do to the domain and range? It flips them, right? So the domain of the exponential is the same as the range for the logarithmic graph. So the range is y as an element of the real numbers. And when you look at the graph and you think about the nature of the function, that makes sense. Y can be anything. such that x is greater than 0 is our domain. And it has a vertical asymptote at x equals 0. Okay, and then again, those properties are all the same for the other version. So this is important because it helps us remember what we're allowed to put in for x and what we might get out, and restrictions for solving equations that we're about to take a look at, that sort of thing, right? When you start to get solutions coming out of these equations, you have to decide, does that solution work? Does it make sense? Thinking about the graph, I think, could be a useful tool. So you can only input positive numbers, but you can get any output. Kind of interesting. Any questions about that? Pretty straightforward. It's kind of familiar, at least, I hope. All right, let's take a look. For the following, determine where y prime equals 0. Calculus students in high school all over the world, they would, if you ask them, how would you describe calculus, or how would you sum it up? Say, take the derivative and set it equal to 0. Like, that's so much what we do in this course, right? Or maybe the second derivative, maybe the first derivative. We're also going to notice that this is something very common that we do in our next unit, which is like problem solving. Where we do that kind of thing all the time as well. So it's a very common thing to do. And so and all the other units, what did we do? We learned how to do derivatives, and then we started setting them equal to 0 to do things with them, like sketching, that sort of thing. So here we go with exponentials. Should be able to do the derivative of that fairly easily, so go ahead. Product rule, so it's the derivative of the first thing, which is x squared, so it's 2x, times the second thing, which is e to the x, plus the first thing times the derivative of the second thing, e to the x, and it's just e to the x because it's just x, so times 1, but we don't need to worry about that. Everybody okay with this? So now we want to set this equal to 0. Y prime equals 0, 2x e to the x plus x squared e to the x equals 0. What do you think we're going to do? Yeah, I can factor out an x, so that's a good thing to do, and an e to the x. So it looks like I'm left with 2 plus x equals 0. So that's pretty much done right there. There's 3 things here. This is the product of 3 things, and each one of those things is like solvable in itself, right? So therefore, x is 0, e to the x is 0, and 2 plus x is 0, which means x is negative 2. And this is where now we revert back to the graph and we think about this and we think, what about all of these? So if x equals 0 or x equals negative 2, that's the input. Can the input of this function, which is like exponential function, so we look here and we see, oh yeah, our domain, x is an element of the real numbers, x can be anything. So any input is fine. Does that make sense? So 0 is good. I can throw 0 at that and it'll work. You could try it if you want. I mean, you could do that in your head pretty easily, but you could always stick it in your calculator and make sure you get a value. And -2, what about that? Yeah, it'll work. If I plug it in. What about this, though? This one, so this one's good too. This guy, that's like the output, I would say, of the e to the x function or of an exponential function, right? It's like the output. When will the graph of e to the x ever equal 0? And it doesn't, so this one's not possible. There's no solution. Okay? So that's a big part of doing these first derivatives or second derivatives or any of the solving equations that we're going to do today is thinking about which solutions work and which don't. Any questions? All right, so we're just going to do a few, some of these are really simple, but just a little bit more practice of kind of rewriting some of these things and working with it. So if you think you know how to do this, go ahead. But this is where you start to get confusing because you're like, oh, wait a minute, is it allowed to be a negative? Is it not allowed to be a negative? You start to think. An exponential graph never goes below the x-axis. It can't be negative. Logarithmic graph does. So that's fine. What's another way that I can think about this? Kayla? Yeah, we can rearrange it. So I can think about the graph and use that as a thinking tool for whether or not there will be a solution. I could also always rearrange it. So this is x, oops, I'm not going to write in green, x equals 2 to the -3, right? So if I rewrite it and go, yeah, I can evaluate that, of course. So x equals 1 over 2 to the 3, which is 1 over 8. Pretty straightforward. What about the next one? See, I told you it'd be kind of an easy day. Very nice. Nothing more complicated than that. And what about this one? Ln just means base e, same thing, like log is base 10, ln is base e. So x equals e to the 5, which works out to, let's see, 148.4, but we'll leave it as e to the 5 as an exact answer. Okay, I hope I'm not going too fast. Ooh, that doesn't look right. Okay, 2 to the 4 log base 2 of 3. So this whole thing is in the exponent. What's going on here? Well, that exponent can just be evaluated, can't it? But there's a trick that I could also do here. So let's do this. X equals 2 to the log base 2 of 3 to the 4. Does anybody know what 3 to the 4 is? 81. And does anybody know what 2 to the exponent log base 2 of 81 is? This is one of those properties that doesn't come up as often. It's 81. So a lot of calculators these days, you can evaluate logs. You can like change the base. So you would be able to type that in 4 log base 2 of 3, hit equals, and it would give you 81. But I didn't even need to do that. With a little bit of properties, it was easy to rearrange and realize that this guy here when you get that, it doesn't come up as often, but when you get that, you can simplify it pretty easily. That might be helpful once in a while. Okay, what about this next one? Similar idea. X equals e to the ln of 5 cubed, because I can take the 3 out front and put it in the exponent. And this is the same property as the last one. Right? It's like, you don't need to write this, but log base e of 5 to the 3, which is 125. The tricky thing about this is there's all these different ways that you can solve it. I mean, we just saw, like, sometimes you have to factor, but sometimes you have a log and you have to solve it, or you have an exponent and you have to solve it, right? There's like all these different kinds. So the tricky thing that people get confused is mixing up the different kinds. So there's a couple ways I can think of to solve this one. Sometimes what we do is we take the log of both sides. Sometimes that can be useful. But in this case, you could also just rewrite it in logarithmic form, right? So that would look like 2x equals log base e, because the base doesn't change, which is ln of 8, and x equals ln of 8 divided by 2. And again, I will leave it there. You could evaluate it if you're asked to on your calculator to 3 decimal places, 4 decimal places, whatever, but for now that's good enough. We good? And this one's like the opposite of that, where we're given the log and we're going to rewrite an exponential. So the base stays the same, e to the 7 equals 2 minus x. Move the x over. And again, whatever that works out to. Any questions? Familiar enough? All right, and one more that's a little bit more interesting. So this is where we start looking at, like, thinking about sketching. Who remembers about critical points or critical values? Where do they occur? And when it doesn't exist. Good. Don't forget that. Sometimes we get rolling where we don't usually have to worry about it, so we start ignoring it. But we want to think about that too. Okay, so let's write that down, where f prime does not exist or f prime equals 0. So let's go ahead and find f prime. Why don't you try that? This is supposed to be, I forgot that there was a mistake in here. This should be an x. Doesn't make a lot of sense as ln of 3. It's not supposed to be a constant. It's supposed to be an x. Makes it a bit more interesting. There we go. So if I've got that 3 around the whole ln of x, then take the 3 down. You still have the ln of x. Exponent becomes squared, and then multiply by the derivative of what's inside, right? Like our chain rule. So it should look like this. And now you have to start thinking about how you're going to solve it. What do you think? Yeah, nice. So 3 over x times ln of x all squared minus 1, I think. Let's set it equal to 0. Ln x all squared minus 1 equals 0. Or maybe I should write it like this. I don't know. What do you think? And now this briefly goes back to MHF again. How do we solve a rational equation like this? We did this in this course too, lots. That whole thing will be 0 just when the top is 0, right? The bottom isn't relevant. So this is 3. In fact, I don't even need the 3. I'm going to get rid of that. So ln of x all squared equals 1. Take the square root. That make sense? Simple equation to solve, I think, but it's one of those things that the better you are at it, you don't have to worry about this step of the process as much, and you can worry about the other stuff. Okay, so we're supposed to find the critical points and the intervals of increase and decrease. What does that mean? That means first derivative chart. So we start when x is less than 1 over e, and then at 1 over e. 1 over e less than x less than e at e and x greater than e. Yes? Where does it not exist? Nice. Now, what else do we know about that? Let's take a look at the graph. So you're saying because there's an x on the bottom, right? So what else do you think about that when you think about 0 and look at that function? What do you think if x is 0? Anything? Anybody have any ideas? We'll look at this more tomorrow, but ln of x minus, cubed. I hope that works. Yeah, minus 3 ln of x. It's got an asymptote there, right? Because of the ln function. So turns out we don't need to worry about that point. And But it is something that you would wonder about, I guess. Does that make sense? Okay, good. So we can write that down. F prime does not exist at x equals 0, but it turns out it's an asymptote. All right, let's move on here. So we got F prime and F. Again, this is a little, so I'm going to use my my calculator, and I'm going to plug in the formula in here because it's going to be a little bit easier to do that, I think. It could be a little messy finding values. Like I got to find a value that's less than 1 over e, but I don't want to use negatives because we saw that that's not going to work, right? In some cases it might, in some cases it might not. So what's a value that I could use less than 1 over e, but that's not going to give me an error? Like this is what I'm thinking of, right? Okay, so I've got bracket ln, actually I'm going to do bracket ln of a squared minus 1 close bracket times 3 and divided by a. I think that's good. So I'm going to pick like just a really small number, like 0.000001. Make sure that it's like, you could even check 1 over e, see what the value is, and make sure that you're getting something smaller than that. And I got a positive. And this is 0. What's a value between 1 over e and e? It's a little messy, but I think it's pretty simple, like straightforward idea. Anybody have a good? What is e? Yeah, 2.7 something. So 1, 2, they would both work. Very nice. If I check 1, I get a negative. And then this is 0 again. And I can just put in some big value, or I could put in 3. I put in 10, whoops. I put in 10 and I got positive again. So it's increasing here, it's decreasing here, it's increasing here, which means if it's increasing and then it's 0 and then it's decreasing, that's a local max. And I'm going to figure out what this value is in a minute, but it's at 1 over e something. And it's decreasing, then it's 0, then it's increasing. This is a local min at e something. And when I plug those into my calculator, I believe I get positive 2 and negative 2. I get nice values at the original, for the original function there. Any questions? Don't forget when you're doing something like that, like if it came up on a test, to actually find the points. You're supposed to find the points. So we usually, not just the critical values, not just where there are critical values, but, and when you say classify, that means like, is it a max, is it a min? That's usually part of the process, right? Questions, questions, questions.